Have you ever imagined a world where AI models could be super efficient without sacrificing performance? Welcome to BitNet, a revolutionary approach to scaling one-bit transformers for large language models. Why are massive language models such a big problem? They guzzle energy and are tough to deploy. But here's the kicker. BitNet changes the game with a one-bit transformer architecture. It uses bitlinear as a simple swap for standard layers, training from scratch with just one-bit weights. The results? It matches top models in language tasks while slashing memory use and power consumption. And get this, it scales just like full precision models, meaning we can go bigger and greener without losing out. This could redefine how we build AI. Check out this figure. It's packed with insights. BitNet, trained from scratch, is shown against other methods like post-training quantization. Notice how BitNet uses only one bit for weights, while others need more. The graph highlights massive energy savings, up to 40 times less than FP16 transformers. And as models grow, these benefits explode. Why does this matter? It means we can build huge, powerful AI systems that are way more sustainable. This isn't just a small improvement. It's a leap forward for efficient computing. This figure caption sums it up perfectly. BitNet trains one-bit transformers from the ground up, delivering competitive results with huge energy efficiency. It beats the best quantization methods out there. And as models scale, the cost savings skyrocket while keeping performance on par with FP16 models. Think about that. Better efficiency without compromise. What could this mean for the future of AI deployment? Ever wondered if human intelligence is really that special? Well, here's a thought. What if all our brain's neurons, the ones behind our feelings and thoughts, actually work in a simple binary way, just like on and off switches? That's a game changer, right? Large language models are getting smarter every day, but there's a huge problem. They're incredibly expensive to run. Why? Because they guzzle energy and need tons of memory, which slows everything down. As these models grow, the data traffic between devices becomes a major bottleneck, making inference slow and power-hungry. So what's the solution? Quantization. It's like compressing a high-def video into a smaller file. It cuts memory use and computation costs while keeping performance strong. Now, most quantization methods are applied after training, which is super easy but comes with a catch. When you push precision lower, accuracy drops significantly because the model wasn't trained to handle it. It's like trying to fit a square peg in a round hole. It just doesn't work well. On the flip side, there's quantization-aware training. This trains the model from the start with lower precision, leading to much better accuracy. It's like learning to ride a bike with training wheels. You adapt early and perform better. But here's the kicker. As precision drops, training gets trickier and might not follow the usual scaling laws. This raises big questions about how far we can push it. In this paper, the authors go all in on binarization. That's the extreme one-bit quantization. Previous work focused on simpler models like CNNs or tasks like machine translation. But large language models are a whole different beast. They use unidirectional decoders and scale up massively, unlike BERT or translation models. So why hasn't anyone tackled one bit for these giants before? That's where BitNet steps in. BitNet is the first to train one-bit large language models from scratch. It uses binary weights and quantized activations, but keeps the optimizer in high precision for stability. The best part? It's simple. Just swap out the linear layers in transformers, plus it works seamlessly with other speedups like flash attention. This isn't just a tweak. It's a revolution in making AI more scalable and energy efficient. So how does BitNet perform? The team tested it on language benchmarks and found it matches full precision models in accuracy and perplexity. But here's the real win. It slashes memory use and energy consumption big time. Even better, BitNet follows the same scaling laws, meaning we can build even larger models without the usual costs. This changes everything for sustainable AI. Ever wondered how BitNet actually works under the hood? Let's dive into Figure 2. Part A shows the computation flow of BitLinear. It's the heart of BitNet, transforming how data moves through the network. Then Part B reveals the full architecture, stacks of attention mechanisms, and feed-forward networks, all powered by BitLinear instead of traditional matrix multiplication. This isn't just a tweak. It's a game changer that makes everything more efficient while keeping performance high. Why does this matter? It means we can build smarter AI without draining resources. Imagine running a massive language model on your phone. Here's the kicker. BitNet uses the same layout as transformers, stacking self-attention and feed-forward blocks. But instead of standard matrix multiplication, it swaps in BitLinear with 1-bit weights. Everything else stays high precision, like 8-bit in their tests. Why not binarize everything? First, residual connections and layer normalization barely add to the cost, so why bother? Second, as models grow, the QKV transformations become tiny compared to other parts. And third, input and output embeddings need high precision for accurate sampling in language tasks. This selective approach keeps things fast and efficient without sacrificing quality. How cool is that? Let's break down BitLinear step by step. First, weights are binarized to just +1 or -1 using the signum function. But here's a clever trick. They centralize the weights to have a zero mean before binarization. This boosts the model's capacity within a tight numerical range. Then, a scaling factor is applied to minimize the error between real and binarized weights. It's like compressing a high-def image into a tiny file without losing the essence. This process ensures the model stays stable and effective, even with ultra-low precision. Now, for activations, they're quantized to B-bit precision using ABSMAX quantization. This scales activations into a fixed range by multiplying with a factor and dividing by the absolute maximum of the input. Think of it as adjusting the volume on your speaker to avoid distortion. It keeps everything in check and prevents values from going out of bounds, making the computation smooth and reliable. A small floating point number is added to prevent overflow during clipping. It's like a safety net, ensuring the system doesn't crash when values get too extreme. This tiny detail makes a huge difference in stability. For activations before nonlinear functions like ReLU, they're shifted into a non-negative range by subtracting the minimum input. Why? It ensures all values play nice with functions that need positive inputs, keeping the network running smoothly without hiccups.
We are Genipad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genipad.com.
Ever wondered how we can make AI models super efficient without losing their smarts? In this part, we're diving into activation quantization. We're quantizing activations to 8 bits for now, saving lower precision for future work. And here's the kicker. We do this per tensor during training, but switch to per token during inference. Why? It boosts stability and efficiency, making everything run smoother. Now, with our quantization equations in place, we can rewrite matrix multiplication. It's like taking a complex recipe and simplifying it step by step for better performance. Imagine we have y equals w times x. This is the basic setup for our matrix operations. Why does this matter for training stability? We assume the elements in w and x are independent and follow the same distribution. This lets us estimate the variance of the output y. It's all about keeping things balanced so the model learns effectively without going haywire. Here's the variance equation. N times var of w times x. This helps us understand how the output fluctuates. Breaking it down further, we get n times e of w squared times e of x squared. This step ensures our calculations stay on track. Finally, we simplify to n times beta squared times e of x squared. This keeps the variance in check, crucial for stable model training. Have you ever thought about why some AI models train smoothly while others struggle? Full precision computations use standard initializations to keep output variance around 1, which is great for stability, but when we quantize, we need to preserve that. So we introduce layer norm before activation quantization. This clever trick ensures the output variance stays similar to the full precision version. In transformers, this is exactly how sub-LN works, making our bit linear layer robust and reliable. Here's the formula for bit linear y equals w times quant of ln of x. It's the heart of our efficient computation, blending quantization with normalization. Let's break down layer norm. It subtracts the mean and divides by the standard deviation plus a tiny epsilon to avoid division by 0. This normalizes the data, and we use beta and gamma to scale and shift it back. Think of it as adjusting the volume on your music player to get the perfect level. Figure 2 shows the computation flow of bit linear. After sub-LN, activations are quantized using the abs-max function. Then, we do matrix multiplication with 1-bit weights and quantized activations. Finally, we rescale the output with beta and gamma to bring it back to the original precision. This whole process is like compressing a file to save space, then decompressing it perfectly when needed. Scaling up AI models is a huge challenge, right? Model parallelism splits computations across multiple devices to handle massive models. But there's a catch. Existing methods need tensors to be independent along the partition dimension. Parameters like alpha, beta, gamma, and eta are calculated from entire tensors, breaking that independence. One fix is to add all reduce operations, but that means more synchronization and slower performance as models get deeper. This same issue pops up in sub-LN with mean and variance calculations. So how do we make model parallelism faster and more efficient? We propose a simple yet powerful solution: group quantization. By dividing weights and activations into groups, we estimate parameters locally for each group. No extra communication needed. This approach speeds things up dramatically, keeping our models scalable and efficient. Here's how it works. Take a weight matrix W with dimensions n by m. We split it into G groups along the partition dimension, with each group having size m divided by G. Then, we calculate parameters independently for each group. It's like having multiple mini-teams working in parallel without waiting for each other. For each group, we compute alpha underscore G as the sum of squared weights divided by n times m, and beta underscore G as the L1 norm of the group's weights. These parameters help maintain consistency and performance across groups. All right, let's dive into this table that shows energy consumption for different models. Why does this matter? Well, it's all about efficiency. BitNet with 1-bit weights uses way less energy than traditional transformers. For example, in a 6.7 billion parameter model, BitNet consumes just 0.02 joules for multiplication and 0.04 for addition, while a 32-bit transformer uses over 4 joules. That's a massive drop. As models get bigger, like 30 billion parameters, BitNet still keeps energy low, making it a game changer for sustainable AI. This table compares energy use between BitNet and standard transformers across various model sizes. It highlights how BitNet's one-bit design slashes energy needs dramatically, which is crucial for building greener AI systems. Now let's talk about group quantization. Have you ever wondered how to handle large matrices without slowing things down? The paper divides weights and activations into groups. Each group calculates its own parameters locally. This means no extra communication is needed, making the process super efficient for big models. Here's how it works mathematically. For each group, they compute values like the maximum absolute value to scale things properly. This keeps everything stable and precise during computations. Moving on to layer normalization. How do we make it work in parallel without bottlenecks? They use group normalization. This technique computes the mean and variance for each group independently. So, no waiting around for other parts. It's all done locally. The formula for layer normalization in a group adjusts the inputs by subtracting the mean and dividing by the variance. This ensures the data stays balanced and avoids issues like exploding values. This approach allows model parallelism to scale efficiently. No extra communication means faster training for huge language models. It's a smart way to handle complexity without added costs. Time to explore how they train this one-bit model. Ever faced a problem where functions aren't differentiable? That's where the straight-through estimator comes in. It's a clever trick that lets gradients flow during backpropagation, even through non-differentiable parts like sine and clip functions. This makes training possible without getting stuck. Here's the kicker. They use mixed precision training. Weights and activations are quantized to low bits, but gradients and optimizer states stay in high precision. Why? To keep training stable and accurate. They maintain latent weights in high precision, binarizing them only during forward passes. This ensures updates are precise and never used in inference, saving resources. One big challenge is the learning rate. With one-bit weights, small updates often do nothing, causing biased gradients. So what's the solution? Increase the learning rate. BitNet thrives with larger rates, converging faster, while full precision models might fail. This simple change accelerates optimization, especially early in training. Ever wondered how much energy your AI models are really using? In this section, we dive into the computational efficiency of BitNet, focusing on matrix multiplication because it's the biggest energy hog in large language models. We're going to estimate both the energy from arithmetic operations and the memory footprint, and trust me, the savings are mind-blowing. Let's talk about energy consumption. Researchers have modeled how much power different math operations take, depending on the bit precision. For example, adding or multiplying numbers in FP32 uses way more energy than in lower precisions like INT8. This sets the stage for why BitNet's one-bit approach is such a game changer. Here's a table that breaks down the energy costs for ADD and MUL operations across different bit representations and process nodes, like 45 nanometers and 7 nanometers. Notice how lower bit precision / energy use dramatically. This isn't just numbers on a page. It's the key to making AI sustainable. In standard transformers, matrix multiplication involves tons of additions and multiplications. The energy formula shows it scales with the dimensions, leading to high costs. But what if we could cut that down? That's exactly what BitNet does. For additions, the energy depends on the matrix sizes and the cost per add operation. It's a straightforward calculation, but it adds up fast in big models. And for multiplications, it's even more intense. Every element multiplied contributes to the energy drain. This is where BitNet steps in to revolutionize things. Now, here's the kicker with BitNet. Since the weights are just 1 bit, multiplications are almost eliminated. Instead, we only do a few scaling operations with small values, slashing the multiplication energy to a tiny fraction. This shift means additions dominate, but overall, the energy use plummets. The multiplication energy in BitNet is calculated based on scaling factors, and it's way smaller than in full precision models. This simple change makes a huge difference in efficiency. And the results? BitNet saves massive amounts of energy compared to FP32 and FP16 transformers, especially in multiplications. This isn't just a minor improvement. It's a leap toward greener AI that could change how we build and deploy models. So how do we test BitNet against traditional models? We trained a range of models from 125 million to 30 billion parameters on a huge English corpus, including datasets like the Pile and Common Crawl. We used the same data and settings for BitNet and FP16 transformers to ensure a fair fight. All the nitty-gritty details are in the appendix, so you can dive deeper if you're curious. Have you heard of scaling laws in AI? They show that as models get bigger, their performance improves predictably, following a power law. This means we can estimate how well a huge model will do just by testing smaller ones. It's like having a crystal ball for AI development. To see if BitNet scales as well as FP16 transformers, we plotted their loss against parameter counts. Amazingly, BitNet follows a similar power law curve, meaning it doesn't fall behind as it grows. We even fit a scaling equation with an irreducible loss term to model this behavior precisely. The scaling law equation includes terms for the parameter count and a constant, showing how loss decreases as models scale up. This isn't just math. It's proof that BitNet can handle big tasks without sacrificing efficiency. Ever wondered how much energy AI models really consume? This figure shows a dramatic comparison between BitNet and traditional FP16 transformers across different model sizes. The lines plot inference energy consumption, and here's the kicker. BitNet's energy use is way lower, especially as models get bigger. Why does this matter? It means BitNet can handle massive models like 30 billion parameters with far less power, making AI more sustainable and cost-effective. The graph highlights that BitNet scaling is more efficient, so you get better performance without the energy drain. Now let's talk about scaling laws. The researchers tested if they could predict BitNet's performance loss as models grow. They used smaller models to fit a power law and then predicted losses for huge 13B and 30B models. Guess what? The predictions were spot on, showing BitNet scales reliably. And here's the exciting part. The gap between BitNet and FP16 transformers shrinks with size. This means BitNet not only matches full precision models, but could even surpass them in larger scales. Why is this a big deal? It proves that 1-bit models aren't just efficient, they're future-proof for scaling AI. Have you ever thought about how we measure AI efficiency? Traditional methods use flops, but that doesn't work for 1-bit models where integer operations dominate. Plus, flops focus on training, not the real-world usage in inference. So the authors introduced something new. The inference optimal scaling law. This law predicts model loss based on energy consumption during inference. Why focus on inference? Because that's where models are used repeatedly, and energy costs add up. The results in Figure 3 show BitNet's scaling curve at 7 nanometers process nodes. Here's the game changer. With the same energy budget, BitNet achieves much lower loss than FP16 models. In other words, BitNet delivers better performance for less energy, making it incredibly efficient for large-scale deployments. But does BitNet actually perform well on real tasks? The researchers tested its capabilities on downstream tasks like Hellaswag, Winograd, and StoryClose. They used both zero-shot and few-shot evaluations to see how BitNet scales. The results in Figure 4 are impressive. As the computation budget increases, BitNet's performance improves steadily. And here's the best part. BitNet's scaling efficiency for these tasks is much higher than FP16 transformers. That means, for the same amount of compute, BitNet learns faster and performs better. Why does this matter? It shows that one-bit models aren't just energy savers. They're powerful learners that excel in practical applications. Training low-bit models can be tricky due to stability issues, right? The authors ran stability tests by varying peak learning rates for BitNet and FP16 transformers. Figure 5a reveals something cool. BitNet converges with learning rates where FP16 fails, showing it's more stable during training. This stability allows BitNet to use larger learning rates, which speeds up convergence. And in Figure 5b, we see that higher learning rates help BitNet achieve lower perplexity, meaning it learns more effectively. So why is this important? Better stability means easier and faster training, making BitNet a robust choice for developing efficient AI models without the headaches of optimization problems. Ever wondered how much energy AI models really use? This figure shows a dramatic comparison between BitNet and the standard FP16 transformer. On the left, you see their zero-shot performance, and on the right, their few-shot performance, both plotted against inference energy consumption. The key takeaway? BitNet achieves similar accuracy levels, but with way lower energy use. That means you get top-notch AI without the massive power drain. Why does this matter? It's a game changer for making AI more sustainable and cost-effective. Here's what this figure is all about. It compares BitNet and the FP16 transformer in terms of performance versus energy cost during inference. The left side focuses on zero-shot tasks where models perform without prior examples, and the right side on few-shot tasks with minimal examples. BitNet shines by delivering comparable results while slashing energy consumption. This isn't just a small improvement. It's a huge leap towards efficient AI that could revolutionize how we deploy large models in real-world applications. Check out this graph on training stability and convergence. On the left, it compares BitNet and the FP16 transformer with the same learning rate, showing how BitNet stays much more stable. Then, on the right, you see BitNet with larger learning rates leading to faster and better convergence. What's the big deal? Stability means fewer hiccups during training, allowing BitNet to learn quicker and more reliably. This is crucial because it speeds up development and makes AI training smoother and more predictable. This figure highlights BitNet's training advantages. The left part demonstrates that BitNet is more stable than the FP16 transformer even at identical learning rates. The right part shows that this stability lets BitNet handle higher learning rates, resulting in superior convergence. Why is this important? It means BitNet trains faster and more efficiently, reducing the time and resources needed to build powerful AI models. Imagine training a model in half the time with better results. That's the power of BitNet. How does BitNet stack up against other quantization methods? In this setup, BitNet is trained the same way as before and compared to top techniques like AbsMax, SmoothQuant, GPTQ, and QUIP. These are post-training methods applied to an FP16 transformer, meaning they reduce precision after training. Some quantize both weights and activations, while others only tweak the weights. BitNet, with its binary weights and 8-bit activations, uses fewer or equal bits than the others. This comparison is key to showing BitNet's edge in efficiency without sacrificing performance. Ready for the results? This table dives into a detailed comparison of BitNet against other methods on benchmarks like Winogrand, StoryClose, and HelloSwag. All models are sized at 6.7 billion parameters for a fair fight. The table highlights how BitNet performs in zero-shot tasks, giving us insights into its real-world capabilities. Why should you care? It shows BitNet's ability to compete with or even beat other quantization approaches, proving that one-bit models can deliver high accuracy while being super efficient. Ever wondered how BitNet stacks up against other AI models in real-world tasks? Let's dive into this figure that compares BitNet with methods like SmoothQuant and GPTQ across different model sizes. On the left, you see zero-shot results, and on the right, few-shot results. BitNet holds its ground, showing competitive accuracy even as models scale from 1.3 billion to 6.7 billion parameters. This is huge because it means BitNet isn't just efficient, it's effective, proving that one-bit models can keep pace with higher precision ones without the energy drain. Here's the kicker. Figure 6 isn't just a chart, it's a game changer for sustainable AI. It visually confirms that BitNet, with its 1-bit weights and 8-bit activations, delivers similar performance to full precision transformers in downstream tasks. Why does this matter? Because it shows we can build powerful AI that uses way less energy, making it accessible and eco-friendly. The consistency across scales means BitNet scales reliably, paving the way for bigger, greener models. Let's break down this table comparing BitNet to other quantization methods. It's packed with numbers on perplexity and accuracy for tasks like Winogrand and HelloSwag. BitNet shines with lower perplexity and solid scores, especially at 1 bit, where it outperforms many baselines. Notice how some methods, like ABSMAX, have sky-high perplexity values. That's a red flag for instability. BitNet, on the other hand, keeps things stable and efficient, proving that 1 bit doesn't mean low performance. This table isn't just data, it's the proof that BitNet is a leader in zero-shot tasks. It highlights key metrics across datasets, showing BitNet's competitive edge. For example, in Winogrand and HelloSwag, BitNet scores are close to full precision models, but with way fewer bits. That's the magic of quantization-aware training. It squeezes out performance without the energy cost, making AI smarter and greener. Why evaluate models across different bit levels? It's all about finding the sweet spot between efficiency and accuracy. This section explains that methods are tested from 16 bits down to 1 bit using zero-shot accuracy and perplexity. Perplexity measures how well the model predicts text. Lower is better. BitNet excels here, showing that even at 1 bit, it maintains low perplexity and high task accuracy. This comprehensive evaluation proves that BitNet isn't just a theoretical idea, it's a practical solution for real AI challenges. So what's the big takeaway? BitNet isn't just competitive. It's a game changer for low-bit AI. It matches or beats other methods, especially at 1 bit, where weight and activation quantizers struggle. Here's the kicker. BitNet's inference cost is much lower, meaning it runs faster and uses less power. This advantage holds across different model sizes, as shown in Figure 6. It proves that quantization-aware training, like in BitNet, is far superior to post-training methods, delivering consistent performance without the energy baggage. All right, let's dive into this table. It's comparing BitNet against other methods like Elastic and ABSMAX in zero-shot and few-shot learning tasks. See those numbers? BitNet consistently scores high across datasets like Winogrand and HelloSwag. For example, in zero-shot, BitNet hits 33.2 on Winogrand, while Elastic lags at 29.6. This isn't just random. It shows BitNet's quantization is holding its ground without sacrificing accuracy. Why does this matter? It means we're getting efficient AI that still performs well in real-world tests. Here's the kicker. Table 4 is an ablation study, folks. It breaks down how different choices affect BitNet. Elastic is another quantization method that adjusts scales dynamically. But BitNet's AppSmax approach? It's simpler and more stable, leading to better performance. And BMT? It's designed to stabilize low-bit models, yet BitNet sub-LN outshines it. This tells us that BitNet's design isn't just clever, it's robust, making it a top pick for efficient AI training. Ever wondered how BitNet stacks up against other methods in real tests? In this ablation study, we pit BitNet against alternatives like elastic quantization and architectures like pre-LN and BMT. Elastic tries to learn scales on the fly, but BitNet's AppSmax? It's more straightforward and delivers better results. In stability, BitNet's sub-LN allows for higher learning rates, speeding up training without crashes. The bottom line? AppSmax and sub-LN aren't just choices. They're game changers that make BitNet stable and high-performing. This changes everything for building efficient models. So what's the big takeaway from BitNet? We've got a one-bit transformer that's not just efficient, it's scalable and stable. It matches full precision models in tasks like perplexity and downstream performance. But here's the kicker. It slashes memory and energy use dramatically, and it follows the same scaling laws, meaning we can build even bigger models without the usual costs. Looking ahead, the team plans to scale BitNet up and test it in other architectures like RetNet. Why does this matter? It paves the way for sustainable AI that grows without limits.